Go ahead and open up window, verify that everything is working properly. All right, bitrate is, that was interesting. It started out very low and turned out quite high. All right, got sound, got everything else. All right, so we're off. This claims we're offline. Preview claims we're online. Fascinating, interesting. I don't know. That's always, it's always a weird thing. Let's go ahead and pop this out. Side, this other side. And we'll do something like that. Okay, but I've got to go prepare for the stream, so I'm going to go you. And I'll be back as soon as I open up some windows and find a chair. All right, I found a chair. Left my glasses upstairs, but that's okay. I'll survive for another morning without them. Okay, so 9:36. Last week on Friday, we went through a little bit. I think, did we finish one of the chapters? We may have. Let's go take a look at what we've got. Awkward. There, that's a better hand position. Let's go to GitHub. Learning Rust. And okay, so currently at generic types, traits, and lifetimes. Ooh, okay, so if we open that up, go ahead and also get a terminal open up. And we can go begin on this. Backends projects mine, learning Rust. Specifically, we're on chapter 9. Right? Is that chapter 9 or is this chapter 10? This is chapter 10. Perfect. So let's actually come on here and we'll do take chapter 10. Oh, we're already in here. All right, so we'll wait until we actually have something to go in. In the meantime, I am sort of taking the day off of work, but I need to keep my eye on Slack over here just in case there's any emergencies that that I'm needed. Averis, good morning for me. Good afternoon for you. It's this Slack channel. All right, so I think things are good so far. I'll just keep an eye on push notifications. All right, so chapter 10, generics. Let's go ahead and get started. And this is the one we're at, right? Generics, types, traits, and lifetimes. Yep, that's it. Every programming language has tools for effectively handling the duplication of concepts. In Rust, one such new tool is generics. Generics are abstract stand-ins for concrete types or other properties. When we're writing code, we can express the behavior of generics or how they relate to other generics without knowing what will be in their place when compiling and running the code. Similar to the way a function takes parameters with unknown values to run the same code on multiple concrete values, functions can take parameters of some generic type instead of a concrete type, like i32 or a string. In fact, we've already used generics in chapter 6 with option t, example 8 with vec_t and hashmap kv, in chapter 9 with result te. In this chapter, you'll explore how to define your own types, functions, and methods with generics. First, we'll review how to extract a function and reduce code duplication. Next, we'll use the same technique to make a generic function from two functions that only differ in the types of their parameters. We'll also explain how to use generic types in struct and enum definitions. Then you'll learn how to use traits to define behavior in a generic way. You can then combine traits with generic types to constrain a generic type to only those types that have a particular behavior, as opposed to just any type. Finally, we'll discuss lifetimes, a variety of generics that give the compiler information about how references relate to each other. Lifetimes allow us to borrow values in many situations, while still enabling the compiler to check that the references are valid. All right, so it looks like we're finally getting to one of these chapters that they were kept on referencing back in the past. And it's going to do like a huge amount of powerful stuff for us, so looking forward to it. Okay, removing duplication by extracting a function. Before diving into generic syntax, let's look at how to remove duplication that doesn't involve generic types by extracting a function. Then we'll apply this technique to extract a generic function. In the same way that you recognize duplicated code to extract into a function, you'll start to recognize duplicated code that can use generics. Consider a short program that finds the largest number in a list, as shown in listing N1. So, okay, so we have our main, let number equals list. We create a vector of integers. We create a mut largest equals number list 0. So we just get the first item in this list. For number in number list. Is that, I guess let mute largest equals number list. So this is just the integer. This is just giving like the first one here, 34. For number in number list. Oh, okay, a number list here. If number, oh, I'm so used to having seen the iterator in here. If number in number list, so like it's going to be this 34. If number is greater than largest, we set largest equal to that number. Print line, the largest number is blah. This code stores a list of integers in a variable number list and places the first number in the list in a variable named largest. Then it iterates through all the numbers in the list, and if the current number is greater than the number stored in largest, it replaces the number in that variable. However, if the current number is less than the largest number seen so far, the variable doesn't change, then the code moves on to the next number in the list. After considering all the numbers in the list, largest should hold the largest number, which in this case is 100. So yeah, like pretty standard reducer here. To find the largest number in two different lists of numbers, we can duplicate the code in listing 10.1 and use the same logic at two different places in the program, as shown in listing 10.2. So we have, okay, so number list here, but then I also see, I don't want you open. All right, that should hopefully remove those push notifications. Sorry about that. Okay, so we have number list, which is of these. For number list, same exact thing. We print line large number, then let number list. So we shadow number list and create a new vector with larger numbers this time. So these can be 32-bit and these can be 64-bit, I believe. Let mute largest. So then we do the exact same code again, though. Although this code works, duplicating code is tedious and error prone. We also have to update the code in multiple places to change it. To eliminate this duplication, we can create an abstraction by defining a function that operates on any list of integers given to it in a parameter. This solution makes our code clearer and lets us express the concept of finding the largest number in a list abstractly. In listing 10.3, we extracted the code that finds the largest number into a function named largest. It's kind of funny that the period is over here. That shouldn't happen. Unlike the code in listing 10.1, which can find the largest number in only one particular list, this program can find the largest number in two different lists. So let's see. We have function largest, list is i32. List is i32, so it's a slice copy of a vector of i32s, returns an i32 number. Let mute largest list equals that. For item and list iter, same exact thing. Then we return largest. Let number list equals this. Result is largest. And then we do it again with number list equals this. Largest. Oh wait, they're the same. The largest function has a parameter called list, which represents any concrete slice of i32 values that we might pass into the function. As a result, when we call the function, the code runs on the specific values that we pass in. In sum, here are the steps we took to change the code from listing 10.2 to listing 10.3. Identify the duplicate code, extract the duplicate code into the body of the function, specify the inputs and return the values, update. Okay, so I was wrong. These are i32 still too. I can never remember what the max on i32 is. Next, we'll use these same steps with generics to reduce code duplication in different ways. In the same way that a function body can operate on an abstract list instead of specific values, generics allow code to operate on abstract types. For example, say we had two functions, one that finds the largest item in a slice of i32 values and one that finds the largest item in a slice of char values. How could we eliminate that duplication? Let's find out. So let's move on. Generic data types. We can use generics to create definitions for items like functions, signatures, or structs, which we can then use with many different concrete data types. Let's first look at how to define functions, structs, enums, and methods using data types. Using generics. Then we'll discuss how generics affect code performance. All right, was just a bunch of people sending stuff. No problems. Okay. In function definitions, when defining a function that uses generics, we place the generics in the signature of the function, where we usually specify the data types of the parameters and return value. Doing so makes our code more flexible and provides more functionality to callers of our function while preventing code duplication. Continuing with our largest function, listing 10.4 shows two functions that both find the largest value in a slice. Right, so we have largest i32 and largest char. So we're sort of doing this work ourselves. We're creating this function, it's taking in this thing. It's exactly the same code inside, it's just what we take in and what we return is different. The largest i32 function is the one we extracted in listing 10.3 that finds the largest i32 in a slice. The largest char function finds the largest char in a slice. The function bodies have the same code, so let's eliminate the duplication by introducing a generic type parameter in a single function. To parameterize the types in a new function we will define, we need to name the type parameter, just like we do for the value parameters to a function. You can use any identifier as a type parameter name, but we'll use T because, by convention, parameter names and rest are short, often just a letter. Really? Well, I guess if we're doing generics, that makes sense. If it's like any other things, I kind of like larger functions, like larger names, to be more explicit about like what exactly it is. Okay, they didn't sign me up for anything, so that's good. Let's see, so we got that. And Rust type naming convention is camel case, short for type. T is the default choice for most programmers. We've had that conversation. I think they're working on changing the word camel case to something else, or camel case, capitalized camel case, because it feels a lot more like Pascal case to me. When we use a parameter in the body of a function, we have to declare the parameter name in the signature so that the compiler knows what the name means. Similarly, when we use a type parameter name in a function signature, we have to declare the type parameter name before we use it. To define the generic largest function, place type name declarations inside angle brackets, sort of like the turbofish syntax, between the name of the function and the parameter list, like this. So function largest, so that's telling it that it's a generic list, then a slice of t, and then return the type. So I wonder if I can make this work before I read on too far. So let's create cargo new generics. And we'll open up code here. Okay, so let's first like pretend we're gonna like pretend our function works, and we're going to create the previous one where we're going to just have an I32. So we're going to say let numbers equals a vector of like 3, 5, 9, 15. And then we're going to say let largest number equals, this is going to be find largest, and we're going to pass it in a reference to numbers. And then we're going to print line the largest number is largest number. Okay, and so that should work, except it's going to yell at us because we don't have the find largest number. So if we say function find largest, this is going to take in a slice of that number. So we're going to say, well, these are numbers, and it's the type I32. We're going to return an I32. And so then we could just do our completely normal reducer here. So let mut largest equals numbers, the first one. And then we want to do a for loop. So for I in, and I'm thinking 1, 2, numbers dot length. Because it's exclusive, we want 1 minus this. So then we can do that. We can say like let current equals numbers of I, and then we'll say if the current is greater than largest, then we want to say largest, set that equal to the current, and then after our for loop, we'll return the largest. Let's make sure this works first before I convert this into a generic. We're going to do cargo run. How's the font on this? Is it a little bit too small, too big? I know it's definitely not too big. I can barely read it in like my second monitor over here, like off to the side where I'm looking at the preview. So I have no idea if that's, it might be too small for like a mobile screen or something. You can make it bigger. There you go. So, okay, the largest number is 15. So that works. Let's come back into here. This bigger. So the idea of what we want to do is we want to then convert this into a generic. So we're going to say t like that, because I believe that's what the book is telling us, that we want this t right here, and then we're going to just replicate this t all over the place. So that's telling us, hey, find largest is a generic. It's taking type, it's a generic type. It takes in numbers, which is a type of, it's a vector with a known type in it, and it returns this type. And so from what I understand, from what, you can only speak for yourself, but it's fine for me. I'll leave it right here unless I need to make it smaller, but thanks, Averis. So from what I understand, the compiler is going to go and rewrite this code for every single type. So it's going to have a find largest that takes in I32, find largest that takes in I64, a float, the two floats, the anything else, characters, strings. And then when I pass it in, it calls the appropriate one for me. So if I run this, I'm getting an error here. Okay. So binary operation cannot be applied to type T. Note T might need a bound for standard compare partial Or, okay, let's get the real error message and then it'll tell us what we need to do. So cargo run. Okay, T might need a bound for standard compare partial order. For more information about this error, try rust-c explain this. Could not compile generics. Okay, so let's try this. A binary operation was attempted on a type which doesn't support it. Let x equals. Okay. Let x equals 12 F32, error binary operation. Okay. To fix this error, please check that this type implements this binary operation. Examples. It is also possible to overload most operators for your own type by implementing traits from standard ops. String concatenations appends the string. Okay, so it's just telling me that it's not really telling me how to do it. Although this might. Oh, that's the left ship operator. Let's see. An implementation of shift left that shifts the left operator on integers to a wrapper around usize. An implementation. Okay, so guess I don't see generics with this one. Oh, here's a generic. T clone. Vector T. Derive partial equal. Is that the one where it's saying? It wants partial order. Associated types. Tons of these. I think what we need is the book to tell us it's. My guess is it's partial order in the derive for this function. So it's let's try it. Let's see what happens. So we start with this. You need to put constraints in your generic types. The function will only accept types that can be compared. Yeah, so I'm thinking that that's what I need to do. I'm wondering if this is the way to do it. I haven't read, like, it's probably going to tell us right in the next section, but I want to sort of try this myself. So we're going to derive, and it's going to be partial ord. Partial ord. Expected item after attributes. Oh, can I not do that just to functions? I only can do that to structures and I can only do this to structures and enums and other data structures, can't I? Can I? I can't do it to functions themselves. So it was a good attempt, but I don't think this is allowed. It's the T trait syntax. Okay, so it's not that. It's the T partial ord in here. Ooh, a nice color. Cannot move out of type T, a non-copy slice. If I move out of here, consider using a reference and stay instead. Okay. If I do that, mismatch types, expected type parameter found T. Expected type T found okay, reference to T. So I need to dereference it here? Nope, that changed it. Can I move out of borrowed content? Expected T because of a return type. That makes sense. This is now mismatch type expected. Okay, let's run it and get the real error message. You could also add the copy constraint. For more information about this error, try rec. Okay, so we need to build a copy. So before I was copying it, and that's why it worked. But then because it's generics, we have to tell it exactly what type, because there are types that don't implement copy, right? So, and it's not making any assumptions, it's making me say like what this is. So T partial order, how can I... Is it just like copy where I can put this in parentheses? And copy the trait? Then if I do that, I don't need the ampersand here. Or here. Expected one of... Okay, so that... You can list multiples with plus. Ooh, okay. Expected one of... Okay, so maybe no parentheses. All right, no red squigglies. Let's see if it works. Ooh, the largest number is 15. Perfect, thank you, Averis. So let's try this again, which is, we're gonna now say, okay, let, we can now say like, let characters equals a vector of, now we'll see if characters works with this, but it's gonna be something like a, E, Z. Let largest char equals find largest, and we're going to pass it, instead of numbers, characters. And then we're going to print line the largest character is char. Now, of course, mismatch types expected a slice array found struct vector vector. Note expected type found type standard vector vector character. Consider borrowing here characters. So we don't, oh right, we don't want to move it in here, I don't think. So this all seems to work. I can totally see why we want to change this to something like it's our array. So you can just say like A for array, or it's like our V for vector. So if we do this, does that work? We should get 15 and Z. So perfect. So that is working the way we want it to. All right, let's come back and see how we're supposed to do it. We read this definition as the function largest is generic over some type T. This function has one parameter named list, which is a slice of the values of type T. The largest function will return a value of the same type T. Yeah, I do agree that list is a better word for this. Instead of V for vector, I'm gonna name this list. Listing 10.5 shows the combined, is this 10.5? Yeah. Shows the combined largest function definition using the generic data type in its signature. The listing also shows how we can call the function with either a slice of i32 values or char values. Note that this code won't compile yet, but we'll fix it later in this chapter. Okay, I'm glad that they mentioned that, because in the past, like, we've seen, oh, just try it, like, and then it's like, oh, haha, it doesn't work yet, and afterwards, and that always bothers me. Okay, so they're doing exactly what we did initially, which is that we put the turbofish syntax with a T here. Then we have our list, %T, and it returns a T. Everything else is the same right now, but they're going to get those errors. So if we compile this code right now, we'll get this error. Binary operation cannot be applied to type T, which is exactly what we got. The note mentions standard compare partial order, which is a trait. We'll talk about traits in the next section. For now, this error states that the body of largest won't work for all possible types that T could be. Because we want to compare values of type T in the body, we can only use types whose values can be ordered. To enable comparisons, the standard library has the standard compare partial order trait that you can implement on types. For more on this trait, you'll learn how to specify that a generic type has a particular trait in a trait bound section. But let's first explore other ways of using generic type parameters. I see what they're doing. They're not fixing that thing. They're saying, well, let's go take a look at this other thing first. Instruct definitions. We can also define structures to use a generic type parameter in one or more fields using the turbofish syntax. Listing 10.6 shows how to define a point struct to hold x and y coordinate values of any type. So struct point. So let's go ahead and implement this ourselves so that we have it. So the idea here is that we have struct point. It's going to take type T, and then x is T, y is T. So it's like, that's how it's going to be the unknowns here. Function main, let integer equals a point, and we could just put whatever we want, whether it's be a normal integer or a float. So let's try it. So we'll have struct. Yeah, struct. Oh, it's it doesn't come in until I put something out here, so it's like points. Okay. And this takes type T, and we're gonna have an X, which is a T, and a Y, which is a T. Of course, all we're getting is that it's just yelling at us that points don't exist yet. So what we can do is down here in main, after we're doing this stuff, we'll also now create points. So we'll say let coordinates coordinate, we'll call this just int 32. This is going to equal to points. There we go. And we're going to hand it an x, which is in 32, so that's like 15, and a y that is like 64. And we could also let coordinates f32 equals, this is also going to be points. We're going also expected expression found closing. Did I do that wrong? All the points. That, I believe, is how you're supposed to be done. Oh, okay. Now it's not yelling at me anymore. Points, and then this is going to be like an x is 13.5, and y is 15.79. And now we can print line coordinates for, we can just derive debug this, right? So what is it? Derive debug? Did I get that wrong? And so coordinates for, well, coordinates I32 and coordinate and F32. And so then we'll just put our coordinates I32 first and coordinates F32. Let's see if this runs or if my derive didn't. Oh, debug. I need to put in that too. Cargo run. Let's see. Could not compile generics. It didn't like this. Okay, so I need to go remind myself how to do the derive debug. So it's Rust derive debug. That's what it looks like here. Can I not do this with generics? Or did I just misspell it? Also, wait, there's no semicolon at the end, is there? All right, what are you yelling at? Does not implement standard format display. Oh, this one also needs to be that. It's multi-line that. Okay, perfect. So now if we come and run it, now it works. So now we get like, yeah, here's the I32, here's the F32, everything just works. Here we are. The syntax for using generics and struct definitions is similar to that used in function definitions. First, we declare the name of the type parameter inside angle brackets just after the name of the struct. Then we can use the generic type in a struct definition where we would otherwise specify concrete data types. Note that because we've only used a generic type to define point t, this says that the point t struct is generic over some type t, and the fields x and y are both that same type, whatever that type may be. This means that if we create an instance of point t that its values are different types, as in listing 10.7, our code won't compile. So yeah, we can't do like integer and float there. In this example, when we assign the integer value to 5 to x, we let the compiler know that the generic type t will be an integer for this instance of point t. Then when we specify 4.0 for y, which we've defined to have the same type as x, we'll get a type mismatch error like this. So yeah, expected, because like this first one got set, right? So then the second one has to be an true integer, not a float. To define a point struct where x and y are both generics but could have different types, we can use multiple generic type parameters. For example, in listing 10.8, we can change the definition of point to be a generic over types t and u, where x is of type t and y is of type u. Okay, so that's interesting. Does the u stand for something? Now all the instances of point are shown are allowed. You can use as many generic type parameters in a definition as you want, but using more than a few makes your code hard to read. When you need lots of generic types in your code, you can indicate your code needs restructuring into smaller pieces. Okay, so if we take a look at this, we do u, this is with a comma, and then the y can be a u, right? So now we can come back down here, and we don't even need this first one, the second one. We can just say coordinates and I'm just going to call this coordinates. I'm going to get rid of u. And we're going to say points 15 and y is 64.0. And I believe that should still work, right? Yeah, so it basically allows whatever type we want. Now, if we want another one, can I just say like A? And this would be like a Z is A. And now for you, we can say Z is maybe the string hello world dot toString, like that. The largest number is 15. The largest character is Z. Coordinates, points. Okay, yeah, it just works exactly how we want. But I could totally see that this causes weirdness here. Now, does the order matter? So I'm doing this in the same order as defined up here. If I say something like this, this is T, and this is A, do we run into problems? Doesn't seem to think it is. No, so I don't think that the order matters really very much. So we can just say this is like T for type, definitely, but then we could just do like U and other things. My phone is blowing up now. Is everything okay? Let's see that. Okay, so interesting things, but okay. And that seems like everything's fine. Okay, so that's actually really interesting. We could probably do the same thing with enums too. And it looks like it's about to go into that section. As we did with structs, we can define enums to hold generic data types and their variants. Let's take another look at option T, enum, that the standard library provides that we used in chapter 6. Okay, so our enum option T, it takes a sum T or a none. This definition should now make more sense to you. As you can see, option T is an enum that is generic over type T and has two variants, sum, which holds one value of type T, and a none variant, which doesn't hold any value. By using the option T enum, we can express the abstract concept of having an optional value. Because option T is generic, we can use this abstraction no matter what type the optional value is. Enums can use multiple generic types as well. The definition of the result enum that we used in chapter 9 is one example. So it's T and E. So now that we know that the T really doesn't matter at all, it's just placeholders. But it's sort of like saying where each thing is going to go, and so it's letting us guess and infer what they are. The result enum is generic over two types, T and E, and has two variants, OK, which holds a value of type T, and error, which holds a value of type E. This definition makes it convenient to use the result enum anywhere we have an operation that might succeed, return a value of some type, or fail, return an error of some type E. In fact, this is what we used to open a file in listing 9.3 where T was filled in with the type standard FS file when the file was opened successfully, and E was filled in with this type standard IO error when there were problems opening the file. When you recognize situations in your code with multiple struct or enum definitions that differ only in the types of the values they hold, you can avoid duplication by using generic types instead. Okay, so method definition. I don't feel a need to like put the enums in there. It feels pretty similar to the structures and how we're going to use it. So, as we did in chapter 5, we can implement methods on structs and enums that have generic types in their definitions. Listing 10.9 shows the point t struct that we defined in listing 10.6 with a method name x implemented on it. So we have our points, implementation for point. It's the same thing, implement type t, function x takes in reference to self, returns a reference to t. Oh, so this is a getter. So this is just a getter for x. Listing 10.9, implementing a method named x on a point t struct will return a reference to the field x, to the x field of type t. Here we've defined a method named x on point t that returns a reference to the data in field x. Note that we have to declare t just after implements, so we can use it to specify that we're implementing methods on the type point t. By declaring t as a generic type after implements, Rust can identify the type in angle brackets as point is a generic type rather than a concrete type. So note that we have to declare t just after implements right here, so that we can use it to specify that we're implementing methods on the type point t. So yeah, we have to fully copy this. We also have to put it here. We could, for example, implement methods only on point f32 instances rather than on point t instances with any generic type. In listing 10.10, we use the concrete type f32, meaning we don't declare any types after implementing. Ooh, so that's actually really interesting. So we don't have to put anything after implement because it's not generic. But this one we do. Okay, that's something I want to play around with. So we have our points here. And what we can do is say implement type t points type t, and then we'll have our function. This is x, and it takes in a reference to self and returns a reference to x, reference to, what is it, t like this? Oh, returns a reference t, so we don't need the turbofish there. And then all we're really gonna do is just use self.x. So in here, if we want to say we have print line coordinates, we can also say print line, we want the x, right? So x is coordinates.x, like that. That should be happy, and we should get whatever those x coordinates are. Expected 3 type arguments. So points t, is that because in here we have, oh, because we have AUA, these needs to be UA. Did you mean T? Do you mean T right there? Okay, so that's interesting because we do implements T. Now, if we do implements U and A here, does that work? Expected reference to T, found type parameter. Expected type T, reference to T, found type A. Oh, because it's X, that's A. Oh, that's interesting. Now what I can do is say, we're just doing this on A. Number of arguments expected 3, found 1. So this one needs, regardless of what this one needs, it needs the t and the u. Cannot find t in this scope. Does it need to be in a certain order too? These are all in different orders now. Expected reference to A, found type parameter, found type U. Oh, wow, okay. So A is now pointing at this one, isn't it? Okay, so having them in the correct order, it is okay with me doing that, but it screws things up. So if I do this, it's now easier to sort of see what things are what. Expected A, found type parameter, found type A, so I need to return a reference to it. And this works. Okay, that's... I could definitely see why this makes it really, really, really crazy. X is 15, okay. So now if I say, another implement. So implement points. But in this case, I don't need to put in the turbofish syntax here, but this points is going to be just on I32s only. Our function, what was x that we got? Or can we not do that? Distance from origin, so whatever that is, F32. So wonder if I could just also have, okay, x that brings in a self. Maybe I'll call it like squared. And this will be a I32. And if we just say, okay, we want self, maybe I'll do squared x. We'll return, so self.x times self.x, but it doesn't know what these are, right? Can I wrap these in parentheses and then do as I32? Wrong number of type arguments, expected 3, found 1, points x, y, and z. Can I do that? No, so I can't do like other type scopes in there. So if I do like I32, oh, so this is telling me that if my points, let's go take a look at this. So implement point F32. But this is for a structure that only takes one thing. So basically it's saying, hey, if we have a structure that they're all I32s, then this function is available for it. However, we don't have that because we have all these 3 different things. So yeah, I could, like, at this point in time, this points, this squared x can only work. I don't even need to as it anymore. I can now just say, hey, if points. So what we can do is let coordinates equals that. But we could also say let coordinates I32 equals points, and we're going to give it like x is 2, y is 4, z is 6. Then here we can print line and say x squared is, and it'll be the coordinates I32 dot squared x, because now that works. X squared is 4, so perfect. So super powerful, very interesting sort of like to play around with, but I can definitely see even with 3 of these it gets just really crazy, because now it's like, okay, there's so many combinations of what things can be, and changing things around in order wise sort of screws things up. It makes it really hard to sort of like figure out what's actually going on. Okay, I didn't see any. Let's get back to what they were trying to tell me what to do here. We've got this stuff. Okay, this code means that type point f32 will have a method named distance from origin, and other instances of point t where t is not of type f32 will not have this method defined. The method measures how far out our point is from the point at coordinates 0, 0, 0, 0, and uses mathematical operations that are only available for floating point types. Generic type parameters in a struct definition aren't always the same as those you use in struct method signatures. For example, listing 1011 defines the method mixup on point tu, struct from listing 10.8. This method takes another point as a parameter, which might have different types than the self point we're calling on mixup on. The method creates a new point instance with the x value from the self point of type t and the y value from the past endpoint of type w. So struct point tu, so we have this point that can be 2 different things, or it has to be 2. Well, I guess like y could be, these both could be like I32s. Implement tu point tu function mixup. This takes in v and w, so like 2 completely different generics. Takes in self that's not referent, so it's owning self now. Other, which is a point bw, which is this thing, so it's a type of point, and returns point t w. And then we're just creating point x self x, y is other dot y. So definitely, I definitely see how that is gonna make like your eyes sort of cross over and go like, what is going on? It's mostly that they're generic, so you don't know what really the values are going to be. You're writing them so that they are you have to have context of what we're trying to do to help make the generics. In main, we have to find a point that has an I32 for x with value 5. And so yeah, this is here's the context for us. That point 1 equals point, x is 5, and y is 10.4. So this is our first one. P2 equals point is x is the reference to string or stir hello, and y is the char c. Let P3 equals P1 mix up P2. So print line P3.x equals P3.y equals. So that's what's going on here, is it's saying like, hey, this other point is the B and W. So yeah, we're getting these other different types here. The P2 variable is a point struct that has a string slice for x with value hello and a char for y with value c. Calling mixup on P1 with the argument P2 gives us P3, which will have an I32 for x because x came from P1. The P3 variable will have a char for y because y came from p2. The print line macro will call p3x equals 5, p3y equals c. The purpose of this example is to demonstrate a situation in which some generic parameters are declared with implement, and some are declared with the method definition. Here, the generic parameters t and u are declared after implements because they go with the struct definition. The generic parameters v and w are declared after fn mixup because they're only relevant to the method. Performance of code using generics. You might be wondering whether there is a runtime cost when you're using generic type parameters. The good news is that Rust implements generics in such a way that your code doesn't run any slower using generic types than it would with concrete types. Rust accomplishes this by performing monomorphization. That's a fun word. Of the code that is using generics at compile time. Monomorphization is a process of turning generic code into specific code by filling in the concrete types that are used when compiled. In this process, the compiler does the opposite of the steps we use to create the generic function in listing 10.5. The compiler looks at all the places where generic code is called and generates code for the concrete types the generic code is called with. Let's look at how this works with an example that uses the standard library's option t enum. So let integer equal sum5, let float equal sum5.0. When Rust compiles this code, it performs monomorphization. During that process, the compiler reads the values that have been used in the instances of option t and identifies two kinds of option t. One is i32 and the other is f64. As such, it expands the generic definition of option t into option i32 and option f64, thereby replacing the generic definition with the specific ones. The monomorphized version of the code looks like the following. The generic option t is replaced with the specific definitions created by the compiler. So yeah, we have option i32, option f64, and then yeah, we're calling these ones down here too. Because Rust compiles generic code into code that specifies the type in each instance, we pay no runtime cost for using generics. When the code runs, it performs just like it would have had we duplicated each function by hand. The process of monomorphization makes Rust generics extremely efficient at runtime. That is super super interesting to sort of like go into and look at. Traits, defining shared behavior. A trait tells the Rust compiler about functionality a particular type has and can share with other types. We can use traits to define shared behavior in an abstract way. We can use trait bounds to specify that a generic can be any type that has certain behavior. Note, traits are similar to a feature often called interfaces in other languages, although with some differences. Defining a trait. A type's behavior consists of the methods we can call in that type. Different types share the same behavior. If we can call the same methods on all those types, trait definitions are a way to group method signatures together to define a set of behaviors necessary to accomplish some purpose. For example, let's say we have multiple structs that hold various kinds and amounts of text. A news article struct that holds a news story filled in a particular location and a tweet that can have at most 280 characters along with metadata that indicates whether it was a new tweet, a retweet, or a reply on another tweet. We want to make a media aggregator library that can display summaries of data that might be stored in a news article or tweet instance. To do this, we need a summary from each type, and we need to request that summary by calling a summarize method on an instance. Listing 10.12 shows a definition of a summary trait that expresses this behavior. Okay, so public trait summary, function summarize, and self, and returning a string. Here we declare a trait using a trait keyword and then the trait's name, which is summary. In this case, inside the curly brackets, we declare the method signatures that describe the behaviors of the types that implement this trait, which in this case is function summarize, send self, and returns a string. After, what's really interesting is like, okay, function summarize, where is that function? Like, we're declaring it. This feels like C's, what is it, like at the top of the file you would write the references to the function, or like tell it what the functions are gonna be down below. After the method signature, instead of providing an implementation within curly brackets, we use a semicolon. Each type implementing this trait must provide its own custom behavior for the body of the method. Oh, interesting. The compiler will enforce that any type that has the summary trait will have the method summarize defined with this signature exactly. A trait can have multiple methods in its body. The method signatures are listed one per line, and each line ends in a semicolon. Okay, so that's actually pretty cool. So we're just saying, okay, this is what will happen, but the actual implementation details are left up to the coder. Implementing a trait on a type. Now that we've defined the desired behavior using the summary trait, we can implement it on the types in our media aggregator. Listing 1013 shows an implementation of the summary trait on the news article structure that uses the headline, the author, and the location to create the return value of summarize. For the tweet struct, we define summarize as the username followed by the entire text of the tweet, assuming that tweet content is already limited to 280 characters. Okay, so we have our public struct news article. So this is assuming that we're in a library here. So public structure news article, we have our public headline, location, author, and content in the structure. Then we have an implementation summary for news article. So, and was it summary was up here? Yeah, public trait summary. So implement summary for news article, function summarize, takes in self, return string. So that's exactly the same as what we had up there. Format, so it does returns the format as string, which is then creating this. Perfect. Public structs tweet. Here's our tweet with this. Implement summary for tweet. Function summarize, which is so it's the same trait but on two different structures implemented in a different way. Implementing a trait on a type is similar to implementing regular methods. The difference is that after implement, we put the trait name that we want to implement, then use the for keyword, and then specify the name of the type we want to implement the trait for. Within the implement block, we put the method signatures that the trait definition has defined. Instead of adding a semicolon after each signature, we use curly brackets and fill in the method body with a specific behavior that we want the methods of the trait to have for the particular type. After implementing the trait, we can call the methods on instances of news article and tweet in the same way we call regular methods, like this. So let tweet equals this, print line, one new tweet, tweet.summarize. So note that because we defined the summary trait and the news article and tweet types in the same librs in listing 1013, they're all in the same scope. Let's say this librs for a crate we've called aggregator, and someone else wants to use our crate's functionality, implement this summary trait on a struct defined within their library scope. They would need to import the trait into their scope first. They would do so by specifying use aggregator summary, which then allows them to implement summary for their type. The summary trait would also need to be a public trait for another crate to implement it, which It is because we put public keyword before trait in listing 1012. One restriction to note with trait implementations is that we can implement a trait on a type only if either the trait or the type is local to your crate. For example, we can implement standard library traits like display on a custom type like tweet as part of our aggregator crate functionality, because the type tweet is local to our aggregator crate. We can also implement summary on vect in our aggregator crate because the trait summary is local to our aggregator crate. But we can't implement external traits on external types. For example, we can't implement the display trait on vect within our aggregator crate because display and vect are defined in a standard library and aren't local to our aggregator crate. This restriction is part of a property of programs called coherence, and more specifically the orphan rule. So named because the parent type is not present. This rule ensures that other people's code can't break your code and vice versa. Without the rule, two crates could implement the same trait for the same type, and Rust wouldn't know which implementation to use. So that's basically like monkey patching that we see in JavaScript all the time, where we can say, hey, let's just change how, I don't know, all strings work. And then anything that happens after that code runs would now be bound by the new rules, which would potentially screw a lot of things up. Is there a trait that we can use here? So I'm thinking maybe we could try a string method on here. I'm not sure if we can make it easy for this, but we could try. So if we can say trait, let's come back here and take a look at how we created that trait. Trait summary. We could just try a trait summary. It's then just the open brackets, and we're telling it what the function is going to look like. So it's going to be like function summarize. It's going to take in a reference to self, and it's going to return a string. And does this trait? No. Okay, so that works. So now in here in points, we have implement points. Let's implement it one more time. So implement summary for, so 4 points. And do I also have to pull in? Now, is you gonna yell at me expected one of? Right, wrong number of arguments. So now we have to bring in T, U, and A. Cannot find T in the scope, so implement T, U, A here. Not all trait items missing summarize. So here we can now have function summarize. This takes a reference to self and returns a string. And what I really want to do, if possible, is just say we're going to return, you can use format. Did I do that correctly? It didn't autocomplete for me. Yeah, I did. And so this is just going to be, okay, X is, Y is, and Z is. And then we'll put in X, I guess it would be self.x, self.y, self. Okay, so A doesn't implement standard format display. A cannot be formatted with the default formatter by using a debug instead if you're using format string. The trait for standard format display is not implemented for A. Consider adding A where A standard format display bound. Note required by a standard format display format for this. So we could try this as well, like the debug, just like it suggests first. And it sounds like we could also bound a trait to maybe like the T, U, and A. A cannot be formatted using question mark because it doesn't implement standard format debug. We have the derived debug, but I don't think, but like it doesn't work with all of those things, I guess. Help, the trait standard format debug is not implemented for A. Consider adding A where A standard format debug bound. Where do I put that in the code? Let's run this. See if it gives me a little bit more. Okay, so A doesn't implement standard format debug. Help, the trait standard is not implemented for A. Consider adding to where A standard format debug bound. But where would I put that? Is that okay? So I'm going to Google search this and let's see if we can find it. No. So all right, let's just go to straight to Google. Put it in here. I believe there's a bug in the derived debug. It's adding a debug bound to the type parameter of error kind, even though it should only be a node ref error. You may just want to manually implement debug. If it is a bug, will this behavior be fixed? Eddie Nectar, welcome to the stream. Why isn't it? Let's see. So that's really interesting that doesn't work. I guess if it was a structure that I was fully creating myself, I could definitely add that in here. And Eddie, I am going to how do I? I want to. I can't move to the other screen because I don't have those things. Gonna time you out for that. Okay, so what do we want to do for points here? Squared x. Okay, so the I think it's telling me that we don't have this debug. This implement the where at, like that sounds like a way to fix it, but I don't know off the top of my head. I think like the general idea would be I could implement this specifically for the debug format to work. You need to constrain TUA with standard format debug. But how do I constrain? We haven't got to that part of the book yet, so maybe in what would it be? Constrain Rust type. Oh, this is the first book. We don't want that. Advanced traits. Okay, so type standard format debug. Use standard format debug. A standard format. Oh, so like we put those traits in here. Or in here. One of the two places. Or maybe both places. So here it would be like, okay, standard format debug. That seems standard or put a for loop in there. Format debug and with A too. Standard format debug. So if we do that, our T now is yelling at us, expected one of, so maybe not here, maybe here. TUA should be TA. Nope, doesn't like that either. Might be easier to use standard format debug before. Oh, do we have to use it too? Cannot find format and standard. So like up here, just use standard format bug. Guess I'm not sure exactly. It's FMT, not format. Oh, okay. FMT. Oh yeah, you had that there. Okay, so no error messages coming out. This is saying is not needed, unused import. So this actually is binding each of these to use these traits. After using it, you could then write T debug, U debug, A debug. Oh, okay, I get what you're saying. So you're saying use standard FMT debug like that. And now we can do T debug, U debug, A debug, and then this works. The cargo run. Oh wait, I have to actually execute this. So we have function summarize on here. I'm kind of surprised that it's not, that we're not like, it's telling me we're not using it. This is on points, right? Yeah. So we now can have print line summarized is coordinates dot summarize. All right, let's try it. Summarized, X is 15, Y is 64.0, and Z is hello world. Okay, so that's actually really cool. That I could see this coming into handy. It is a little bit difficult to sort of read and like get used to. Let's see, I got some more push notifications. Not seeing, okay, nothing bad here. But yeah, that is pretty cool. Implementing a trait on a type is similar to implementing regular methods. The difference is that after implement, we put the trait name that we want to implement, then use the for keyword, and then specify the name of the type we want to implement the trait for. Within the implement block, we put the signature methods that the trait definition has defined. Instead of adding a semicolon after each signature, we use curly brackets and fill in a method body with a specific behavior that we want the methods of the trait to have for the particular type. After implementing the trait, we can call the methods on instances of news article and tweet in the same way we call regular methods, like this. So yeah, that's sort of what we did. Note, oh, did I go back? Is that why? Yeah, we already read through that stuff. Default implementations. Sometimes it's useful to have default behavior for some or all of the methods in a trait instead of requiring implementations for all methods on every type. Then, as we implement the trait on a particular type, we can keep or override each method's default behavior. Listing 10.4 shows how to specify a default string for the summarize method of the summary trait instead of only defining the method signature, like we did in listing 10.12. Public trait summary, function summarize self, string from. Okay, so that's interesting. The problem that I see with mine is that, well, it might work. I think the big thing is because the generics might mess it up a little bit. Let's go on and see how it's used. To use a default implementation to summarize instances of news article, instead of defining a custom implementation, we specify an empty implementation block with implement summary for a news article. Okay, so I think that's the way we do here. So implement this for points and then an empty block. So it would basically be like this. And now up here for trait summary, type string, we then have this, right? Let me make sure. Yeah, okay. So then this one is just going to be saying, okay, we want to return format, and it's going to be the X is, Y is, and the Z is. Now, of course, this is like very, very specific to this specific summarize, so it would be better to make them do that, but I sort of want to play around with this. So it's going to be self.x, self.y, self.z. So if I save that, no field X on type self. Now, is that because I can't find it here? Let's try running and getting self.x, self.y, self.z. Okay, so I think we have implement type TUA for point summary for points. And then we have summary, which takes in this self. But I think the problem is because of they're not giving us examples with generics here. So I'm thinking that using generics for this is not really the best idea. So I'm going to put it back. This should all work again. If we had something that wasn't generic, then we could definitely do that. Okay, so to use a default implementation of summarize instances of news article, instead of defining a custom implementation, we'd specify an empty implement block with implement summary for news articles. You cannot access fields and trait definitions. Not all types that implement the trait will have the fields you expect. Yeah, I can imagine that. Oh, so like that's what this is saying, is it's just going to return a new string like this. So it's you don't have access. You don't really have access to self then, do we? Like, not really. The code prints new article available, read more. Creating a default implementation for summarize doesn't require us to change anything about the implementation of summary on tweet. In listing 1013, the reason is that the syntax for overriding a default implementation is the same as the syntax for implementing a trait method that doesn't have a default implementation. As of now, there's no way to require fields, but I think there is an RFC. Oh, so that would be interesting because then we could write traits for that, but I could also see, like, why bother if it's so specific to a structure, then just put it in that structure. I could definitely see that argument also being made. Default implementations can call other methods in the same trait, even if those other methods don't have a default implementation. In this way, a trait can provide a lot of useful functionality and only require implementers to specify a small part of it. For example, we could define the summary trait to have a summarize author method whose implementation is required, and then define a summarize method that has a default implementation that calls a summarize author method. So public trait summary, summarize author, and then summarize. Okay. Oh, interesting. So they're using each other. To use this version of summary, we only need to define summarize author when we implement the trait on a type. Implement summary for tweets. Right, because then we only need to implement that. That is here for us, unless we want to like overwrite it. Yeah. Have we seen this at character before? Is that a formatting character or is that something else? After we define, or is it actually, that's actually for the tweet. So never mind, that's just a plain character. Never mind. After we define summarize author, we can call summarize on instances of the tweet struct. And the default implementation of summarize will call the definition of summarize author that we've provided. Because we've implemented summarize author, the summary trait has given us the behavior of the summarize method without requiring us to write any more code. A great example for that is the iterator trait. You only have to implement the next method and get all the other iterator methods like map for free. Yeah. Okay, so then we can just use it and it's all good. Note that it isn't possible to call the default implementation from an overriding implementation of that same method. All right. Trait bounds. Now that you know how to define traits and implement those traits and types, we can explore how to use traits with generic type parameters. We can use trait bounds to constrain generic types to ensure the type will be limited to those that implement a particular trait and behavior. For example, in listing 1013, we implemented the summary trait on the types news article and tweet. We can define a function notify that calls the summarize method on its parameter item, which is of the generic type t, to be able to call summarize an item without getting an error telling us that the generic type t doesn't implement the method summarize. We can use trait bounds on t to specify item must be of a type that implements the summary trait. Okay, so function public function notify t, so takes the summary greater than symbol item t. So that's really interesting. Does it talk about that here? I'm not seeing it use that here at all. So public function notify takes an unknown t, the generic summary. Okay, item T. We place trait bounds with the declaration of the generic type parameter after a colon and inside angle brackets. Oh, this is the other side of the angle bracket. Never mind. I'm used to a space. Yeah, I don't know why I thought that was greater than. I just missed there not having another one. Because the trait bound on T, we can call notify and pass in any instance of news article or tweet. Code that calls the function with any other type, like a string or an I32, won't compile because those types don't implement summary. So we're saying, take in any generic, but the type has to implement summary in order for us to use it. So we kind of did that here, didn't we? Somewhere. Where we say, hey, find largest takes in any type as long as it implements partial order and copy. Then we take an item with type unknown, a generic type, and then we do our breaking news items.summarize. So that's awesome. We place trait bounds with a declaration of the generic type parameter. Okay, so after colon inside angle brackets, because of the trait bound on T, we can call notify and pass in any instance of news article or tweet. Code that calls the function with any other type, like a string or an I32, won't compile because those types don't implement summary. We can specify multiple trait bounds on a generic type using the plus syntax. For example, to use display formatting on the type T in a function as well as the summarize methods, we can use T summary plus display. To say T can be any type that implements summary and display. However, there are downsides to using too many trait bounds. Each generic has its own trait bounds, so functions with multiple generic type parameters can have lots of trait bound information between a function's name and its parameter list, making the function signature hard to read. For this reason, Rust has alternative syntax for specifying trait bounds inside a where clause after the function signature. So instead of writing this, so function signature display plus clone, u clone plus debug, we can use a where clause like this. So some function tu, all this stuff, where t display plus clone, u clone plus debug. Oh, that's interesting. So that's what I was trying to say. It was trying to tell me to use where for it. So in here, we're using this trait debug, a debug. So I might be able to take this. Oh, nope, don't want to go too far. Right here. Remove these. And of course, it's going to yell at me because we don't know what that is. But I can say where. And then it's just, okay. T is debug. Wonder. Oh, yeah, display plus cone. So debug. So then I kind of want u to be, come on, u is debug. And a is debug. Not all trait items implemented missing summarize. Well, okay, so it's there. So this is not implemented correctly. Oh, this isn't a function? You have to move this down like that. Expected expression found keyword where, so it doesn't like this either. So some function tu I32. So we have all of this, but it doesn't like the where. So I guess we can't exactly use that. And I was kind of also hoping that we could put this up in here. It doesn't like this either, because then it's saying, okay, do I have to use semicolon to end it? No, because expected one of const create default extern. Okay, so it's not, it doesn't like where here either. Can I put this in here with the semicolon? Nope. So no matter what, it doesn't like this. One thing, oh, okay, wait, it's before, it's after this I32, before the opening of the bracket. Okay, I'm starting to see that. So this gets moved down. This gets moved down to here. Not all trait items implemented missing the summarize. Summarize is right here. That's a comma. Implement has stricter requirements than trait. Implement has extra requirements. T standard debug. Implement has stricter requirements than trait. Implement has strict extra requirements. Oh wait, can I put it here in between this? Let's put this all back. All right. So what I want to do is remove you, and I'll create you like that. Okay, now it's working. I just didn't know where to put it properly. So implements TUA summary for points TUA, but then we have this where, and we can move them up properly into here. So now we're just to see like, hey, these are all implementing debug. I do see that this is kind of like a little bit, it makes this not have the same feel as the rest of the functions. But it works. Let's double check that it works. Yes, it does. Okay. Fixing the largest function with trait bounds. Now that you know how to specify the behavior you want to use using the generic type parameter bounds, let's return to listing 10.5 to fix the definition of the largest function that uses a generic type parameter. Last time we tried to run that code, we received this error, which we've already fixed in our code. In the body of largest, we want to compare two values of type t using the greater than operator. Because that operator is defined as a default method on a standard library trait, standard compare partial order. We need to specify partial order in a trait bounds for t, so the largest function can work on slices of any type that we can compare. We don't need to bring partial order into scope because it's in the prelude. Change the signature of largest to look like this. So function largest, t, partial order, that's sort of what we have, except we also ran into the problem where we need copy. So then we get this error. The key line in this error is cannot move out of scope t a non-copy slice. With our non-generic versions of the largest function, we were only trying to find the largest I32 or char. As discussed in stack only data, copy section in chapter 4, types like I32 and char that have a known size can be stored in a stack. So they implement the copy trait. But when we made the largest function generic, the list parameter could have types in it that don't implement the copy trait. Consequently, we wouldn't be able to move the value out of list 0 and into the largest variable, resulting in this error. To call this code with only those types that implement the copy trait, we can add copy to the trait bounds of t. Listing 1015 shows the complete code of a generic largest function that will compile as long as the types of the values in the slice that we pass into the function implement the partial order and copy traits like I32 and char do. So we already have this in ours, but basically we have our partial order plus copy. If we don't want to restrict the largest function to the types that implement the copy trait, we could specify that t has the trait bound clone instead of copy. Then we could clone each value in a slice when we want the largest function to have ownership. Using a clone function means we're potentially making more heap allocations in the case of types that own heap data, like string. And heap allocations can be slow if we're working with large amounts of data. Another way we can implement largest is for the function to return a reference to t value in a slice. If we change the return type to %t instead of t, thereby changing the body of the function to return a reference, we wouldn't need the clone or copy trait bounds, and we could avoid heap allocations. Try implementing these alternate solutions on your own. Okay, using trait bounds to conditionally implement methods. By using a trait bound with an implement block that uses generic type parameters, we can implement methods conditionally for types that implement the specified traits. For example, the type pair t in listing 1016 always implements the new function, but pair t only implements the command display method if its inner type t implements the partial order trait that enables comparison and the display trait that enables printing. Okay, so we have struct pair t that has x and y there t. So a very simple structure. They're both going to be the same type. Implements t pair t, function new. Okay, so basically we're just creating a new one. Implements t that has display plus partial order, pair t. So only if the values that we put in there have display type, and if we put it in there that has the partial order type, then we can have command display that takes in self if self.x is greater than self.y, the largest member. Okay, so then we have these prints that are in here. We can also conditionally implement a trait for any type that implements another trait. Implementations of a trait on any type that satisfies the trait bounds are called blanket implementations and are extensively used in a Rust standard library. For example, the standard library implements the toString trait on any type that implements the display trait. The implement block in the standard library looks similar to this code. So implement t display, so toString for t, okay? Because the standard library has this blanket implementation, we can call the toString method defined by the toString trait on any type that implements the display trait. For example, we can turn integers into their corresponding string values like this because integers implement display. Right, yes, that makes sense. Traits and trait bounds let us write code that uses generic type parameters to reduce duplication, but also specify to the compiler that we want the generic type to have particular behavior. The compiler can then use the trait bound information to check that all concrete types used with our code provide the correct behavior. In dynamically typed languages, we would get an error at runtime if we called a method on a type that the type didn't implement. But Rust moves these errors to compile time, so we're forced to fix the problems before our code is even able to run. Additionally, we don't have to write code that checks for behavior at runtime because we've already checked at compile time. Doing so improves performance without having to give up the flexibility of generics. Another kind of generic we've already seen is called lifetimes. Rather than ensuring that a type has the behavior we want, lifetimes ensures that references are valid as long as we need them to be. let's look at how lifetimes do that. So let's come in here and look where we are. So it looks like we're about to get into 10.3, validating references with lifetimes. So I'm going to copy this. I am going to bring the stream down to a close, but let's go ahead and sort of like clean up after ourselves. All right, so let's first come down here and we're going to edit our README. Specifically here, so change till you. I'm going to do chapter 10. That. Let's go get a link here. There we go. Okay, so that's where we're currently at. Let's close and save that. Let's also push this code up to GitHub. So our README and everything else. So this is going through chapter 10, which is traits and generics. And let's go ahead and push this on up. Okay, perfect. So now all that code is up there. Let's also go and maybe we'll start closing these down and seeing what we have. So you don't need view anymore. Okay, so we have the constrain rest type. We already got that in here. The drive debug, that sort of, we needed to implement that on everything. I don't think we needed this either, because, yep, and then we got our lifetimes we're about to do, and here we are with our code. I don't think we have anything to add into the wiki at this time because we've got all of our examples inside of chapter 10 generics here. Okay, so we've got that. I'm going to close that down, and so that just leaves us here. So anyways, everybody, thank you for stopping by and watching the stream. It's been awesome fun. I was hoping to be able to get through all of chapter 10, but I'm going to have to go and get ready for lunch and go do some other things today. However, it was awesome doing an extra long 2-hour stream. I have the code that you saw me write. I uploaded that to GitHub. I have a link to that in the sort of the channel descriptions. So either in YouTube, it's going to be in the description of the video, or here on Twitch, it's going to be on my my channel description, which should be below, or you have to click to find it depending upon if you're on mobile or not. I also generally tweet out on Twitter when I'm going to be live. For example, I think early this morning, I sort of woke up and realized that I hadn't had enough sleep, so I delayed the stream a little bit, but then it was a little bit longer. So if you're following me on Twitter, you'll see those notifications pop up. Otherwise, if you just want live notifications when I go live, follow me here on Twitch. Also, follow me on YouTube when videos are uploaded there as the archive. So that way you don't have to watch them live. Again, thank you very much. If you have any suggestions or responses, or you're just going through this as well and you want to leave a note, send me a tweet, leave a message for me on YouTube for the video, or anything else. Anyways, thank you very much, and I'll see you tomorrow morning at 7 a.m. Mountain Time. And with that, we're done. Have a great rest of your day.